La Gran Columbia University, Reading Plan for Math. The beauty of maths. Mathematics is at its heart the study of patterns, structure, and regularity. As such, it has long been the central tool in understanding, organizing, and making sense of data. Now, in a world in which we confront the information glut, it's increasingly important to extract useful information from huge sets of data. To do this, a large area of research is fast developing called machine learning, an area that is proving hugely useful as well as fascinating in its own right. In medicine, for example, automated techniques to aid diagnosis to predict prognosis based on experience will be a great use to doctors and their patients. In engineering applications, we want computers to perform cognitive type tasks such as recognition of handwritten letters or digits or facial recognition. For a security or fraud detection application, systematic detection of anomalous behavior will be increasingly useful. And we want better spam filters that will, on the basis of experience, such as record of users blocking particular messages, recognize and reject junk email. At their core, all these problems involve some or all of the following generic tasks. Classification of data into two or more types of classes using as a guide the known classifications of some previous data. Clustering of data into similar groups. Detection of unusual data that is outliers. Given the commonalities between these and other applications, there is much to be gained from developing general techniques for solving the generic tasks identified. Since many of these data sets from which we want to learn or infer patterns are enormous, ad hoc techniques are just not useful. What is needed are principled, probably effective methods which are also efficient in the sense that they can work quickly enough to be of practical use. This is where machine learning comes in. It is a large area of research activity involving mathematicians, statisticians, computer scientists, engineers, and others working together to develop efficient general procedures or algorithms for tasks such as these. Many very general machine learning paradigms have been developed. Some have their roots in classical artificial intelligence closely related to mathematical logic. Others look to biology for inspiration. For example, there was a huge surge of interest a couple of decades ago in artificial neural networks. Popular methods include support vector machines, decision trees, and, as has long been the case, increasingly sophisticated statistical methods. In all of these developments, mathematical analysis is essential. Modeling, learning, or pattern recognition tasks inevitably involves the theory of probability if one is to be able to say anything useful. Analyzing the effectiveness and efficiency of the algorithms requires discrete mathematics and computational complexity theory. To date, the most successful approaches have drawn together a variety of techniques and ideas from a range of advanced mathematics, including probability theory, combinatorics, geometry, and algebra. Although it's interesting to note that the mathematical world might inform or provide theoretical underpinning for the development of general learning algorithms, which may then be potentially useful in real-world applications, that is not the primary motivation for mathematicians. What really fires mathematicians is that the problems that arise are very often interesting in their own right. In seeking to solve them, we can appreciate what Bertrand Russell described as the stern perfection of mathematics. Like much university research, this work is theoretical, but as Carl Lewin and others have said, there is nothing so practical as a good theory.
Created using Powtoon.